What is a qubit? Qubits are quantum bits. They are used to encode information in quantum computers and are analogous to bits in classical computing. Classical bits take the value of either 0 or 1, but a qubit may be in the 0 or 1 state at the same time by superposition. So to understand qubits, we first have to discuss superposition and quantum entanglement. In quantum mechanics, superposition describes a particle existing in multiple states at the same time. This is due to the wave-like properties of particles at the quantum scale. They may overlap and exist in multiple states simultaneously until it is measured. Think about tossing a coin. When it's in mid-air, the state of the coin is both heads and tails. It's only when it lands that the side of the coin is decided. The landing is equivalent to a quantum state being measured. Entanglement describes the dependence of the properties of one qubit on another. Take a look at these two entangled qubits spatially separated into closed boxes. When a measurement is performed on one system to find out its state, like momentum, position, or polarization, for instance, this would instantaneously decide the properties for the entangled system too. These properties enable quantum computers to process calculations simultaneously because they reduce the number of steps required to complete an action. So quantum computers allow advancements in areas including communication and cryptography. Now that we know a little bit about qubits and how they work, let's go a little further and find out how they are made. There are various platforms for qubit generation, including trapped ions, quantum dots, NV centers in diamonds, etc. But superconducting qubits are currently the most advanced qubit technology and is used by most quantum computers today. Superconductors are materials that do not show resistance below a characteristic critical temperature, where electrons would flow infinitely without energy loss. Now, to maintain quantum coherence, and hence the quantum mechanical properties of qubits, the electron-electron interactions must be maintained. Fortunately, in the case of superconductors, electrons condense into electron-electron pairs called Cooper pairs due to phonon creation at low temperatures. Now, most superconducting qubits use what is called a Josephson junction, a non-linear and non-dissipative conductor. This non-linear property is what makes Josephson junction particularly useful, because it indicates that the energy level spacing is unequal. This prevents the excitation of higher energy states and allows scientists to address only the lowest two energy levels as a qubit, accomplishing the isolation of a two-level quantum system. Now, Josephson junctions consist of a metal-insulator-metal sandwich, typically composed of aluminium superconductors and an insulating aluminium oxide. This structure is essentially two superconducting electrodes separated by a very thin tunnel barrier. The insulating material in the Josephson junction has an energy gap greater than the typical energy difference between the two levels in a qubit, so the Cooper pairs do not break and the quantum coherence can be preserved. Meanwhile, the insulating layer is very thin, by a few nanometers, which allows effective tunneling through the insulator. When the Josephson junction is connected to regular linear capacitors, the circuit can now create an LC resonator, which can behave as a qubit. Scientists can control qubits by controlling their energy states, which allows them to manipulate quantum information. The energy state of the electrons will be determined by their spin orientation, so controlling the spin would lead to controlling the electron properties. A strong magnetic field is first applied to the spot we have previously identified in the material using a superconducting magnet. This will align all electrons in the spin-down state, at which they have the lowest energy. Then, a pulse of microwave with a specific frequency, depending on the magnetic field, can be applied. This would excite the electrons to the spin-up state. In the process of excitation, however, the microwave can be stopped at any desired point. In other words, by stopping the pulse at a specific moment, we can create a desired quantum superposition with a specific phase between the spin-up and spin-down states. Unfortunately, there are still some critical limitations to quantum computing. The two biggest challenges are coherence time and error correction. Qubits are very sensitive to the environment they sit in and may accidentally be quote-unquote measured not long after they are created. By measured, I mean the qubit collapses into one state as its information is transferred to the external world, so the qubit will lose its coherence. Quantum error correction is one way in which scientists are trying to solve this problem and improve the accuracy of quantum computers by preventing noises that cause the decoherence. This is an extremely difficult job, partially because one is not allowed to measure the qubits directly to check for errors. Scientists are still working to improve the level of error correction, but the very need for error correction perhaps indicates that quantum computers still have a long way to go. Thank you for your attention.